About daylight. Yeah, we are here at Bartenbach. One slide about Bartenbach. We are lighting design and research and development office. Meanwhile, we are private also now, but meanwhile we are bought by EGLO, so we are part of a big group. Okay, we have also an academy, and Bartenbach is famous for lighting engineering, artificial light, daylight, etc. So some basics. I like this as a physicist. If we look at the sun radiates in 1 hour roundabout. You can do it. A very simple calculation. In 1 hour, the sun radiates as much energy to the Earth as mankind needs the whole year as primary energy. So, and similar it is with light. We would have enough daylight if we only exploit 2% of the incoming daylight. This would be enough to have a mean illuminance on the tables of 500 lux. Okay, this is only philosophy. It should tell us that we have enough resources. The sun is an exhaustless energy and light source for mankind. Of course, we know, we come back to this later on, we have some problems to exploit this, because of course, for example, the daylight, the distribution in time and on Earth is not the same than the need of daylight. And this causes some problems. Okay, this should tell us that the exploitation of daylight is the most sustainable or alternative or renewable energy exploitation than we can do. If we transfer radiation power into electricity, and then electricity again into light, we have two transformation processes with a lot of losses. And okay, I didn't know that this is animated. And if we use this light directly to illuminate rooms, then we can avoid, in principle, all these losses. Of course, we are well aware that this is a challenge to exploit the direct sun and the diffuse sky light in a way that it serves also for comfort, for energy savings, etc. You see, where are the challenges to use daylight? Daylight is a very flexible or time-dependent source. It depends on the time of the day and the year. It depends on the weather. It depends on the location on Earth, etc. So, as an example here, this is the spectral distribution, spectral power distribution of the incident light on the horizontal plane. This is sun plus blue sky. This is only the power distribution of the blue sky, and this is the power distribution of the sun. So the spectral distribution is very different, and it changes all over the day and the year. And also the intensities are changing, of course, from night, where we have almost 0 lux, until more than 100,000 lux during the day. You can see here, this is Bartenbach's facility. We are looking to the west, and you see here we have a blue sky. Here we have a partly cloudy sky. Here we have a more or less cloudy or diffuse sky. This is fog. And so perspective. Yeah, in a fisheye perspective, we can see the distribution over the whole hemisphere, which causes the illuminance. And we are now going to the requirements. We need, of course, nearby the facade, usually it shouldn't be a big problem to have enough daylight. But the problem is if we go deeper into the building, into the room, usually, I think I have here, I have a curve, a principal sketch. You have a daylight factor nearby the facade, which is very high, but in 4 or 5 meters depth, you have only 1%. Yeah? Here you can have 20%, and here you have 1%. So here you have really a lack of light, yeah? And a very uneven distribution. So this is the first point, the distribution, of course, the amount of light also. And at the same time, you would like to have a view to the outside, and you have to protect against glare, because the luminances here are around about 100 times higher, even in a cloudy sky, than the luminances inside. So you have adaptation problems, yeah, and you have physiological or psychological glare here. Yeah, there are also energetic aspects, of course. In summer, usually here in Europe, in Middle Europe, you have to protect against the sun to avoid overheating. In winter, it would be fine to use the incoming energy to heat the building. In summer, usually you have the problem of overheating, and you need a lot of energy for cooling. So you have to control not only the lighting, the light flux, you have also to control the energy flux. And you have to control this in a situation where the outside situation is very, how to say, flexible, very changeable. So this is a big challenge for the technique to meet all these requirements. Of course, meanwhile, we have also these circadian and melanopic lighting issues. We could use daylight also to stabilize this circadian rhythm, also to increase performance, mood, cognition, etc. So we have a lot of different requirements, also sometimes contradictory requirements, and these requirements are changing because the outdoor situation and sometimes also the indoor situation, dependent on the use of the room or type of the room, is changing. So these are the challenges we have to meet when we would like to exploit daylight. So it looks easy and it sounds reasonable to exploit daylight, but in practice there are a lot of barriers. Yeah.
Yeah. To also realize these facts and to fulfill these requirements, you need the appropriate daylighting systems, and what Wilfried showed before, to adapt for this situation where you have not sufficient light in the depth of the room and high luminances at the facade. You need to account for that using daylight redirecting devices, daylight redirecting systems to account for that and really generate the proper daylighting distribution in the rooms. All these requirements in the meantime also found their way into the European standard. There's it was established in 2017, 2018, and came in effect in all European countries. And with this for lighting designers and for architects, it is now mandatory to fulfill these requirements the lighting standard, the daylighting standard gives for all buildings in Europe, and they more or less mimic and represent exactly those requirements. There's prerequisites in the standard that give you a baseline for daylight provision. How much light do you need? How much daylight do you need to have in your room? And how do you need to have it distributed in your room, that you have it more or less homogeneous distributed in your room. You need to have a view out. It is specified how much view out, what you need to see, which kind of layers from floor, from ground out of, from sky, from buildings and surroundings, what do you need to see from that? Exposure to sunlight, getting back to the first speaker, to Thomas, it's an important thing, also the exposure to sunlight, to also give people enough sunlight even if they're indoors, especially in rooms, not in office rooms, but in other rooms, in living rooms, in schools, in patient rooms, in hospitals, and so on. And another important, the fourth important part is to protect from glare. So if there is sun, but also if there's high luminances from cloudy skies, you need to provide proper daylight shading and sunlight shading to protect from glare situations. To do all that, daylighting designers and architects, they need to account for that, and they need to prove that they meet this standard with their designs. And so this is what the current design work is doing simulations to be able to do that. And this is something where Bartenbach is also very active in this field, doing a lot of research in this field, in daylighting simulations, bringing it to the next level, and really being able to do daylighting simulations for all kinds of architectural buildings and all kinds of systems. Within the last years, and also with the new requirements in the standard, it is now important to not only look into very specific situations, and this is what Wilfried said at the very beginning. Daylight and sunlight is very flexible, very changing, a very variable light source. And to account for that, it's not sufficient to only look into a sunny condition and into a perfectly diffuse condition, but we need to look into the overall year and to really know in the simulation what happens in the overall year, and how the building and the daylighting in the building performs over the year. So this is what's happening and what is in the development, really giving tools to architects, to lighting designers to do daylighting simulations, annual daylighting simulations, and really perform these kind of evaluations throughout the year to get daylight illuminances and daylight luminances for glare evaluations throughout the whole year. To do so, there's different methodologies that are developed, and where we have also been involved quite a lot in doing these kind of things. Going back one slide again, if you think about that, the overall year has 8,760 hours, and daylighting simulations, lighting simulations in general, are a very computationally demanding task. So doing a brute force simulation of more than 8,000 simulations, or 4,000 daylight hour simulations, this would never end. So there are methodologies and new versions to do these kind of simulations on a metrics-based method to improve that and to speed up that calculation that allows you, even for these kind of complex buildings like the one you see here, to really do these kind of annual daylighting simulations. To be able to, as we said before, you need to account for the requirements by using also daylighting systems. And a main problem and a main challenge in daylighting simulations has always been to use daylighting systems also in the simulation. And here there's a lot of work going on in the international community working on daylighting simulations to account for these kind of systems, and to not, as you see here in the left image, not really use the geometry, but use a computational description, the so-called BSDF description for that, to do these kind of simulations and be able to do these quick and efficient annual simulations. as we said, glare and view are important topics in the requirement and also mirrored in the daylighting standard. It is important to evaluate for that in simulations as well. So looking into this new approach with using these kind of data sets, there are problems in doing glare and view evaluation through that. So there are also new methodologies that can help you really gain new and better simulations and better approximations of the real world situation for these simulations. So what is done here, and this is something that we have been working on quite a bit in the last time, to also be able to really, there is, and fabric shades, this is one of the very most used daylighting systems for glare protection. If you want it like that, it is quite a simple system. It is just some fabric that you put in front of your window. From the computational side, is one of the most complex systems that you can imagine. As you can see here on the left, there is a part, there's a view through part. You need to account for that. There is some scattering going on around the sun that can cause glare issues if you really have it in the field of view. And to really appropriately account for these kind of fabrics and of these kind of daylighting systems, it's important to use the corresponding algorithms in the simulations. As there's really a lot of need on that, and there's also a question going back again to that, how to really simulate that and how to really simulate glare from these kind of systems. It is important to perfectly match what is really seen and what is the sensitive and the important size of that glare scene that you see here of that sunspot. And so here at Bartenbach, we're also doing fundamental research in that area to find out what is the relevant size of this sun and this glare effect that we see in a window. So just to show that from here. Another short topic to look into, it's all a simulation part, but if we look into daylight, and this is what also Wilfried mentioned earlier, it is important to not only look into the lighting, but also into the energy part, that the daylighting system and the facade system in general, it is the barrier between the indoor and the outdoor world. So it is important for the lighting performance in the room, but also of the energy performance. And that's why it's really important to look into that as well. What we did here is we set up something together with partners from Zumtobel and from the University Innsbruck. We said there is a lot of tools out there. If you have a sketch, an early design situation, a very early idea of a building, and you already want to have answers about the daylighting situation, but also about energy questions, heating, cooling, electric lighting, the comfort in that scene. How does that look like? The problem is there are a lot of tools out there to do all these kind of calculations, and they perfectly work if you have complex situations and if you have a detailed model already. But if you are in that phase that I just showed before, in very early design phase, just showing this sketch, there is not really a solution for that. So this was for us the starting point to think about how can we do that and how can we get a first guess, what is the best system, what is the best facade for this kind of idea that we have for this location, for this building. And so together with our cooperation partner, we came up with this idea of having a very simple tool that gives you results within a couple of seconds and really tells you something about the lighting, but also about the energy performance of a building or a room. So in the end, we came up with a tool, and I really invite you to test it out. It's a free online tool that is also used to educate and to tell people, if you think about daylighting and if you think about facade systems, also think about energy and also think about the connection of daylighting and electric lighting and energy and comfort of the users indoors in terms of overheating, but also in terms of luminance and glare. And how important it is, only a very short comparison of different systems showing that what you do in the facade, it really matters to the building in terms of energy, what you see on the left side. Depending on which kind of system you use, the final energy demand really changes. But also the daylight autonomy changes with that, but also the view and the glare, the luminance exceeding as a metric for glare. You see that there is a high difference in what you do and what you solve with the different systems. Which kind of systems can you use here? And here only very quickly some ideas and some systems that Bartenbach has been developing over the last decades in the meantime already. There are ideas to really use, and what we show in the sketches before is to really redirect light into the depth of the room. You need to work with mirrored surfaces, with mirrored systems that help you really guide daylighting and sunlight into the depth of the room, onto the ceiling of a room, and with this into the depth of the room. Different shapes are possible for that, with different specific performance indicators that they have. The one you can use also as a system where you can look through. The other one has a perfect glare protection, bringing it with it, or you can use prismatic systems for redirection or for sun shading. So there's really a lot of these systems that can be used. And Wilfried will give us an overview of projects where these kind of daylighting questions have been solved. And these systems have been installed.
Yeah, David, thank you. This is a very old example. It's called SBV Biel. Biel is a town in Switzerland, and this project is more than 30 years old. It's an extreme project, but you can see the principles. We divide the facade here in two parts. The lower part is for looking through, and for glare protection we have a screen which is removable, and the upper part is a redirecting prism system which redirects the daylight, here the diffuse or the cloudy skylight, onto the ceiling, and the ceiling is covered with high, more or less high specular aluminium. And you see the luminance, the brightness here is much higher than here, because the daylight, the skylight is redirected into the depth of the room. So, and additionally to this redirecting, to this daylight exploiting system, we have a sun shading system. This is to shade against the sun, to protect against overheating. And these are prism lamellas. They are movable on by a horizontal axis, and following are tracking the sun and give a perfect redirection. The sun paths hit this system and are redirected back. Yeah. So the G value here is almost 0. So we have a perfect sun shading. More or less the function of the whole facade is very good. But of course, you can see it's architecture, and it's a big technical effort, and maybe there are different opinions about such an architecture and such a system. Yeah, so it's a big effort. A similar, a very extreme example is in Wiesbaden, a German town, the ZVK. Here on the facade is a movable system, and here it's opened for cloudy days where no sun hits the facade. We open the system, and this is a redirecting louver which redirects the diffuse skylight into the building, into the room. And if the sun in a clear sky hits the facade, we close the system. I think in the next slide we can see it better. Yeah, here this is for the cloudy sky, and the light is redirected into the room and building. And here in a sunny situation, it's closed, and part of this shade is made by special lamellar systems which redirect the direct sunlight into the room, onto the ceiling, and into the depth of the room. We can see this in the next slide. You see, this is really direct sunlight. Otherwise, you wouldn't have these sharp shadows. And you see here, these are the sun lamellas redirecting the direct sun onto the ceiling. And the other part is closed. And the lower part is open to have a view to the outside. It's really an extreme solution. Also from a functional point of view, it works very good. The room is very well daylit, sunlit here. And yeah, you don't need any artificial light. And I forgot to argument also, the sun shading is also perfect because we only use as much sunlight as we need for illuminating the room. So here in this case, we never have an overheating problem because the energy you need for illuminating, you also have inside the room if you use artificial lighting. Yeah. So it's not a problem of overheating. This is the Stadtbücherei Augsburg in German also. Here you see special, how we call this, David?
Light trumpets.
Yeah, genau, light trumpets. This is calculated. This is not an accident here, these different triangles. It's calculated in the way you see the patterns here. The patterns, the sun patterns are moving here with the sun. And this is more an aesthetical or emotional aspect. It opens the room. It's really dramatically the effect. I was there also. And you have the emotion. You are really free here. Yeah, you have no surrounding walls, etc. You are inside in the inner part of the building. And this is an old method to give this impression to stairways in buildings. Yeah? But also here are the libraries. Okay, they are well illuminated over the ceiling. I have no slide here, further slide about the other part of the facade. In the facade here, we have also redirecting lamellas, high specular lamellas, which redirect the light into onto the ceiling and into the room. Yeah, this is another project. Maybe David.
I can explain a little bit on that. It's a novel project in Germany as well, Adidas Headquarters, and the interesting and important part of that is it's a huge glass facade, and with glass facades you usually have the problem that you have overheating. So it was very important to have a proper and an efficient sun shading around the whole building and around the whole glass facade, and this is what came out here. With this specially designed structure, you really can, depending on the orientation of the facade, these elements, they are not equal. The four sides of the building, they don't have the equal shape in the facade. They look similar, but they are not equal. They have different opening, which is accounting for a different sun path that you see on the relevant facade. And with this, you can really generate a very efficient glare protection and not glare, sun protection system for this facade. This is a detail from that where you see that you have an angular dependent sun protection that really gives you, for different positions of the sun, you have different G values through that architectural structure, and it provides a very high, a very good G value, very good sun protection for that overall huge building with the fully glazed facade. Another example of a very good daylighting solution is, and everyone is invited to visit us here in Alrans, in our R&D building that you can see here. We have a big south facade on the one side, and on the northern side we have skylights additionally to that, and we really have very high daylight illuminances throughout the day. We did also the simulations. This is something you do not measure that, but you can but you can simulate that. We have a daylight autonomy, so over the whole year of more than 80% in that whole in the whole building, and we get really a huge daylight autonomy here that provides us with very low artificial lighting demand that we need. Really, only if we have very motivated workers come in the morning or leaving quite late. So there's the need for artificial lighting, or in winter times when it's getting bright later and getting dark sooner again in the evening. But there's really a huge effect on that we can use that. The whole building is also equipped as a living lab, so we have a lot of monitoring possibilities in here that we use to monitor and show also the possibilities that you can do with proper and intelligent daylighting design. For the electric lighting in here, supporting that, and that also goes hand in hand with the talk that we heard before, it is important that if you need lighting in the evening, then you should do the right thing to not disturb your circadian rhythm and to disturb your melatonin and cortisol and other hormone suppression and rhythms. So we have that human-centric lighting concept also in the building, where we can produce, if we have quite dark, foggy, rainy days outside, we can produce high illuminances during the day, up to 1200 lux on our tables, and going down with color temperature in the night down to close to 2000 Kelvin to really avoid melatonin suppression during nights. A very last slide, just to highlight and summarize more or less, again, also summarizing together from what we heard before, and really promoting again how important it is and how good it is to use daylight, and also to see daylight not only as lighting, but it's really a kind of renewable energy source that we have. It is unlimited available, it is efficient, and we can just use it anytime it is there. We heard before there are a lot of positive effects on people in terms of sleep, in terms of hormones, in terms of mood, and it can help us also to reduce energy demands for electric lighting on the one hand, but also, and maybe even more important nowadays, for heating, and more important for cooling of systems if we do a proper sun shading. So with this, we would like to conclude, and thank you very much for the attention, and we're happy to take any questions.